In this lab, we are going to talk about peanuts. See, what other class can you take where you learn all of the things that are necessary to get you through life each and every day? And peanuts are one of those, right? So we're going to talk about peanuts, but more importantly, we're going to talk about an advanced laboratory technique called the Soxhlet extraction and the Soxhlet extractor. So this is the laboratory glassware that you're going to be using to basically do the job that the Soxhlet extraction is going to require. But before we do that, I'm going to give you a little lesson about peanuts as a whole. So peanuts first, they're produced widely throughout the world. Peanuts, 46 million tons are produced each year. Could you imagine swimming in a sea of 46 million peanuts at one time? But the problem here is that peanut is called a nut, but it's not really a nut. Oh, we've been lying to you since you were little. Peanuts are actually seeds. They're not nuts. It's an edible seed. And if you toast them, they're very good. And if you boil them in the state of North Carolina, people seem to kill each other over them. So peanuts are widely accepted and widely used throughout many different cultures. Peanuts take about 4 to 5 months to mature, and because of that, they are replenishable and they can grow, and we can harvest them quite easy without a problem. China, India, and the United States are the top producers of peanuts, so we are in the top 3, and all of the growth with the peanut happened in the early 1900s. And the reason is because someone discovered peanut butter. So someone realized that they can take a peanut and basically make peanut butter out of it, and then they started sharing what all you could do with the world of peanut butter, and people began to kind of latch on to this topic, latch on to this new concept, and really it has been a staple ever since the early 1900s. You know, we see very many food trends come and go, and those food trends typically could stay around for a couple of months before people realize, oh my God, you're getting heart attacks because you're on this new diet, or for a couple of years before they go out of fashion and something else comes around that's a little bit better. Peanut butter was also used in candies back in the day, which made it even better, and plant oils were also used during World War I. The person that was all kind of leading the peanut army back in the day, his name was Dr. Washington Carver, and he helped really begin this peanut boom that we started to experience in the very early years of the 1900s. The reason that peanuts came into the picture is because cotton was a very important, if I could say, crop during that time. The problem with cotton, though, is that it removed almost all of the nitrogen from the soil. And nitrogen is one of those components that you have to have in your dirt in order to make it grow stuff efficiently, right? So cotton was a problem. Cotton was really mass planted everywhere and harvested, and we had to do something to replace the nitrogen content. Well, this could be things like fertilizer or some other natural type of source, or this could be crops that basically would put nitrogen into the soil themselves. And this is where peanuts came into play, because peanuts replenished the nitrogen that was removed by the cotton back in the day. So these fields would get rotated, and you would put cotton out for a while and you would grow it, and it would take all the nitrogen out of the soil, and then you would plant peanuts instead of cotton that year, and then peanuts would give the nitrogen back to the soil, and then you could rotate back in the cotton, which could grow without a problem after that. So that was kind of the common thing that was done back in the early 1900s. George Washington Carver, here he is. And the reason that I want to show you a picture of him is because a lot of times throughout the course and throughout sciences, you typically see old white men that are leading the charge in the sciences, whether that's chemistry or botany or physics or geology or chemistry, whatever the case is, it's old white men that are doing it, right? However, George Washington Carver is really the first time that we see a black man kind of leading the charge into this field of chemistry. He was a botanist, though he was not a chemist by trade, and he was born into slavery. 1861 to 1864 is the roundabout year that they basically think that he was born. There's not an exact date, but they're thinking within these couple of years, that's kind of the time frame where he came on board and began to bless us with his presence on Earth, right? So he helped construct over 100 recipes using peanuts. He did this to encourage the planting of the peanut, and that way, if people knew what they could do with the crop, they would be more than willing to plant the crop and kind of try out these new recipes like peanut butter and some candies related to peanut butter that goes along with it. George Washington Carver was never married, and rumors had it that he was bisexual. So at 70 years old, he began a very strong, quote, friendship with a person named Austin Curtis Jr. And Austin Curtis Jr. was a very young black man. He was a graduate of Cornell. He had previous teaching experience. And George Washington Carver, with his strong friendship to Austin Curtis, basically pulled some strings a little bit and helped give Curtis his own teaching gig at the college that George Washington Carver taught at. After George Washington Carver passed away, though, what happened is that they let Curtis go from the college, and rumors state that he was actually fired. He was not persuaded to resign. They actually got rid of him after that point. Here's a picture of George Washington Carver to the right-hand side, and then Austin Curtis over here to the left. So these two men were very, very close. When you saw one, you saw the other. They did many things together, in public at least. And then rumor had it, because of that and because he was never married, then he was probably bisexual. And this could have been his life partner in his very late stages of his life. All right, so food allergies. Well, peanuts are very common food allergies, right? Don't pay attention to the gluten. All right. The problem here is that celiac disease, which is the actual disease that's caused by gluten, less than 1% have that in the United States. So if people go in and say, oh, I can't eat gluten, well, then you want to smack them on the cheeks a little bit and say, well, you probably don't have an allergic reaction to gluten because you're probably not 1% of the American population that has celiac disease, right? But some people do, and some people do need to stay away from gluten, but now it seems like people stay away from gluten because it's the thing to do. Ooh, gluten-free, let me try it. Well, peanuts are a different story. Peanuts cause a severe allergic reaction to a very large population of people, at least larger than the gluten people. So we're talking about 4 out of every 100 children have a food allergy, and that food allergy we have to pay attention to. And peanuts are estimated to basically target 4 million people. And these are very life-threatening. It will literally close people's esophagus off, and they cannot breathe anymore if they are exposed to peanut or peanut oil. So because of that, these people typically carry around EpiPens, and that's kind of what you see here in the center of the picture. So if they do come out with some kind of an attack, they've got a backup that they can basically shoot themselves with the EpiPen, and that takes care of the allergic reaction that they might have. So over here to the side, percentage of children under the age of 18 who had reported a food or digestive allergy in the past 12 months. The total number, 3.9, and then less than 5 years, 4.7, 5 to 17 years, 3.7. You can see the breakdown between male and female. It looks like the females have a more reporting of allergies than males do. And then if you look at the racial breakdown, non-Hispanic, Black, and then Hispanic. It looks like if you're Hispanic, then you don't have as many food allergies as the rest of the populations, right? So good news for you if you are a Hispanic male that's between 5 to 17 years old. So that's the best population to be in if you do not want a food allergy at all. Now, because we're talking about peanuts, and because we're talking about allergies, we also need to talk about peanut oil. Very often you go through a drive-through and you might get a McDonald's French fry and you'd be like, I can't really make these French fries like this at home. What do they put in the McDonald's French fries to make me keep wanting to go back and keep eating them? They have to put some kind of drug in it, right? Well, Chick-fil-A is also very commonly known for their waffle fry. And not just the waffle fry, but the taste of the waffle fry that they use. And one of these reasons is because they use peanut oil. Oils make the world of difference when it concerns frying product. Whether that's fried chicken, or French fries, or fried green tomatoes, or fried mozzarella sticks, the type of the oil that you use becomes very important. There's peanut oil, there's canola oil, there's vegetable oil. There's all different types that are out there on the market in today's consumer shelves, right? So peanuts are made of natural the peanut oil basically comes from peanut, and the percentage breakdown here is about 48%. So if you take peanuts and you weigh them and you extract the oil from them, about 48% of that weight is going to be the oil from the peanut itself. Oils can be extracted for a many number of reasons. Most of the time cooking, but these peanut oils and vegetable oils, these can be extracted for a number of different purposes. There is a preservative that's added to it. Oils can go rancid, just like milk and just like any type of food product. So they want it to stay on the shelf, and they want it to stay on the shelf a little bit longer, so they put a preservative in it. And the preservative for peanut oil is typically vitamin E. Vitamin E does a very good job to kind of make sure that the oil doesn't go rancid and bad after it goes out of the supplier and onto the shelves of the grocery store. So what we're going to be doing in this laboratory is we're going to take the raw peanut and we're going to dry it out to get rid of the water. And then from that point, we're then going to take the peanuts and we're going to extract the oil from the actual peanut itself to end up with peanut oil. And this is what you would see in the grocery store, right? Here's a big old jug of peanut oil. And if you are buying the peanut oil to cook with, well, you need to be my best friend, because this jug will typically cost anywhere between $10 to $15, depending on the size that you're buying. And if you've got the money to spend $10 and $15 on a jug of peanut oil to fry your stuff in, then we need to hang out a little bit, and you need to take me out and buy me some drinks maybe. So you're my new best friend. Over here to the side, that's a big old vat of peanut oil that they're probably getting ready to deep fry something in. I mean, that's all that we do in the South, right? We deep fry food. If it can be deep fried, we eat it. Whether that's deep fried chicken or deep fried turkey or deep fried Oreos or deep fried Twinkies, we're going to find a way to deep fry it to make it even better. And over here to the right-hand side, you're going to see a poster, and it says, peanut oil will make medicine, soap, salad oil, shortening for the home front. So this is giving people a reason to grow peanuts in their fields, at their plantation homes, while they sip sweet tea sitting back on their front porch. So why not kind of persuade them to do what you want them to do with it? Now, what about vegetable oil? What about this canola oil stuff? What about the fake butter that you might see on the grocery store shelves in the refrigerated section? What is all of that stuff? Well, these are classified as fats and oils. That's what they are, right? Peanut oil, vegetable oil, canola oil, they are oils by definition because they're liquid. Fats are solids. So that would be something like lard. Ugh, disgusting. Or real butter. Now I say real butter, not the fake butter, but real butter would be a fat. Most fats, you might want to write this down, it might show up a little bit later, but most fats come from an animal source. So, hey, I can take a pig and I can chop it up and butcher it, and then I can render parts of it down to give me lard, right? Animal fat. That's what a fat is. It typically comes from an animal. Oils typically come from a plant. So that's why we see canola. That's why we see vegetable. That's why we see grapeseed. That's why we see peanut oil, avocado oil. Those are all typically coming from a plant origin. So if I want to take a look at the structures of what these are, over here to the left at the bottom of your screen, that is basically symbolic of a fat. We call this structure very condensed. And these fats are solids because these big long tails is what we call them. So imagine up here at the very top where these red balls are, those are carbons, the black ones that sit down below them. The red ones are oxygens, okay? So the way that this structure is ordered is that we have a big long tail of carbons that come off of that major carbon up here at the top, the head of the molecule. And then we have a big long straight chain of carbon that comes down through here. And we have another big long straight chain of carbon that comes down through the third one. And because there's three of them, we call that a tri. And because it's in the world of fats and oils, and because it's made from glycerol, which you're seeing on the middle of your screen, that is why we call them triglycerides. So triglycerides, that's what they are. It's a 3-carbon chain made from glycerol, and those hydrogens have been replaced by big, long carbon tails that basically stick out of the side or at the end of the molecule. If those carbon tails are perfectly flat against each other and they touch each other at multiple locations, think of cigars here, very long, narrow pieces that you can stack together and they touch in many, many different spots. That is what we would call a fat, and that makes things a solid. Well, the difference in the chemical structures here is that if we throw in kinks to those big long tails, and you can kind of see here to the right, it looks like it starts to go down, and then all of a sudden, bloop, it kinks out to the left. And this one goes down, and bloop, it clicks off to the right. This one's got a kink in it too. Well, they don't really overlap. They don't touch as much as they do in the fat molecule. And because of that, the melting points go down. And because the melting points go down, we end up with liquids, not fats, which are solids. All right? So melting point has everything to do with whether you have a solid, a liquid, or a gas. And with that in mind, the melting points are based on how much the molecule touches each other. And if the molecule touches each other, and we call that van der Waals forces, then these van der Waals forces skyrocket the melting points up, which gives us higher melting points, and that gives us solids. Okay? Now, let me kind of write that out for you a little bit. So, let me clear this off, and we're just going to kind of sum up a very important kind of property that we just talked about. And this is called van der Waals forces. DER, van der Waals forces. So if I've got a molecule, and let's say I've got 3 carbons here, and these carbon tails, there's 1, there's 2, and there's 3. If those carbon tails are pretty much straight, then they're going to touch at many different places. So I'm just going to kind of draw like a shape around them, like an eclipse almost. An eclipse, an ellipse. All right, elliptical shape. And those areas are allowed to touch. I mean, they're pretty straight. They can touch from top to bottom. They overlap each other pretty well. Well, that means that van der Waals forces are in place. And what are van der Waals forces? Well, van der Waals forces are things like hydrogen bonds. Okay, and hydrogen bond is a hydrogen that's attached to an N, an O, or an F that's then attached to another N, O, or F on a molecule. So that's the definition of a hydrogen bond. So hydrogen bonds, very, very important. Some of the other things that kind of go in with this are covalent bonds. And when we talk about covalent bonds, that means just with association, okay? That means a part of the molecule is negative, part of the molecule is positive, and because of that reason, they kind of touch and they hang out a little bit. They're not really permanently attached. It's not really a permanent charge that's on the molecule. It's just an association with each other. Opposites, slight opposites in this case, attract. Okay, those are what we are talking about. And then finally, one of these is called London dispersion. So that should be an L, London dispersion. And London dispersion basically just means a random point in time where we get a charged molecule. Okay, so basically what this is saying is that this is typically nonpolar. It's made up of carbons and it's made up of hydrogens. So there's no free electrons really anywhere in those tails to give us a charge. It's pretty nonpolar from beginning to end, right? So what causes them to be attracted to each other? Well, let's think that this is that big long carbon tail. You've got to keep in mind that electrons are associated with it. So there's electrons that are all the way around this big long carbon tail. And they move, and that's the point of electrons. They're not rigid. They're not stuck in one position. They kind of move and fluctuate throughout the molecule. That's how organic chemistry works, okay? So these electrons, because they constantly move and fluctuate through a molecule, then at some point in time, randomly, at some point in time, statistics is going to say that maybe, just maybe, some more electrons might be over here on this side because they're moving around versus what's on the other side over here, right? And when that happens, this side becomes negative, partially negative, and this side becomes partial positive. That's what we call a London dispersion force. So electrons move freely. It just so happens that the electrons might be lopsided at some point in time, and when that happens, it creates a temporary negative and a temporary positive charge. And you know what? Here's the thing. If there is another one of these big long carbon tails that are beside of that, and if this carbon tail or molecule does London dispersion and we get a partial negative and a partial positive, a chain reaction is going to happen. And it will make this neighboring molecule or carbon tail basically force all of its electrons on this side because this is now positive, and those negative electrons are going to be attracted to it. And we see a little bit of glue, a little bit of bonding that happens because of that random temporary force that happens in these molecules. Okay? Well, the issue here is if we go back to the solid and the liquid, let's say that we have a molecule now, and these molecules are not completely straight. Let's say that there is a double bond in these tails or these carbon structures. When this happens, it puts a big kink out into that carbon tail. And we see funny things that can happen when the double bonds are formed into the pitcher. It makes things go crooked. And this is how we get a liquid and not a solid. And that's what the two structures down here are basically telling you about what's going on. Okay, fats and oils, like we said before, oils typically come from plant products. So peanuts are plants. Plants give you oil, so we have peanut oil. They are composed of a triglyceride with fatty acids that cannot pack tightly together. It decreases forces of attraction and causes them to have lower melting points, which is why they're liquids. And we can talk about hydrogenation with oils. And we will go back and we will talk about what hydrogenation means. It was presented in organic chemistry, but if you've not taken organic chemistry yet, hydrogenation is completely new to you, and we need to talk about it. So that's what we'll do in the next video. We'll talk about hydrogenation, and we'll talk about the Soxhlet extractor after that.